Welcome back. We're now going to talk about optimality conditions for convex problems. And we're going to start with the perhaps simplest case for problems that are differentiable and unconstrained. So in other words, I'm interested in the problem minimize f of x. And I want to know, what can I say about a solution x hat to this problem? So this is something that we have all been accustomed to using back from our calculus, early calculus days. How did we solve a problem? Our major tool was just take the derivative, set it equal to 0, and solve. The same thing is going to hold here. It's not going to be quite as easy for us, but still what's useful is to obtain a characterization of optimality. So x hat is an optimal solution to this problem if the gradient of f at x hat is equal to 0. Simple enough. We can see that this is the case either just by reasoning it out, so maybe in high school you proved it, or probably you just said that it's flat is what the derivative being equal to 0, and that must be a minimum point. But we can just directly use our definitions of convexity. I should say this is for f convex. Everything we're talking about for now has this property. So remember definition 2. Definition 2 of convexity said that f of y is greater than or equal to, in other words, f convex is equivalent to f of y greater than or equal to f of x plus the gradient of f of x times y minus x. Well, what happens if the gradient of f of x is equal to 0? So let's apply this definition for x hat. If the gradient of f at x hat is equal to 0, the above definition reads simply f of y is greater than or equal to f of x hat for all y. Well, that's exactly what it means to be a solution to the problem minimize f of x. We've seen this property in many cases before. Let's use just some very simple examples. If you have numbers a1 to an, I want to find an x to minimize 1 over n times the sum of ai minus x squared. What do? Take the derivative, set it equal to 0. What does this look like? I get 2 over n times the sum of ai minus x. Chain rule also brings a minus sign. Set this equal to 0. I can divide through by any constants, and I get that the sum of ai minus the sum of x is equal to 0, or in other words, the sum of x is equal to the sum of the ai's, or n times x is equal to the sum of ai's, or finally that my solution is just the average of the ai's. A simple application, but still important. This tells us that the mean has an interesting characterization. The mean is the value that solves this optimization problem. Something a little more interesting. Ordinary least squares, we get vectors, we get data yi and xi. Again, xi could be in Rd. Remember now, when we talk about statistical problems or machine learning problems, there's often this change of variables. In optimization, we really like x to be our function that we're optimizing over. In statistics or machine learning, oftentimes the convention is to use beta or theta, and I'm just going to follow that convention here. So ordinary least squares asks me to minimize 1 over n times the sum of yi minus xi transpose beta squared. Again, beta is what I'm minimizing over, and I can write this as 1 over n times the norm of x beta minus y squared. This is also equal to 1 over n if I expand out this Euclidean norm, beta transpose x beta minus 2 beta transpose x y plus y transpose y, take the derivative, set it equal to 0. So the gradient of this is equal to 2 over n times x transpose x beta minus twice x y plus 0. Set this equal to 0, and I get that beta hat is equal to x transpose x inverse x transpose y. These are our familiar normal equations. These are the easy cases. This characterization in this case, just like in many of problems from when we learned calculus, is enough to solve the problem. That's not going to be the case for most problems we care about, but it is still very useful to have a characterization of what an optimal solution is. What about non-differentiable functions? For non-differentiable functions, we no longer have the derivative. I want to minimize f of x. The condition here is very similar. X hat is an optimal solution if 0 is an element of the subdifferential of f at x hat. Remember, what is a subdifferential? This is called the subdifferential. G is an element of the subdifferential of f at x is equivalent, again, everything in sight is convex. F of x is convex. Is equivalent to writing that f of y is greater than or equal to f of x plus gx times y minus x for all y. Our picture, some sharp point. At a point that's where we have smoothness, there's a unique vector, namely the gradient, which allows me to approximate the function with a linear function that always lies below. But at a point, I can do better than that. But at a point, we see that there are potentially multiple vectors g. G would be the normal vector in this case of what I'm trying. And this is the case where the subdifferential doesn't have just one unique element, the gradient here, but it has potentially more than one. So again, just plugging in, if 0 is in the subdifferential at x hat, then the above reads, the definition reads, f of y is greater than or equal to f of x hat plus 0 for all y. In other words, x hat is an unoptimal solution. I'm writing un because I'm guarding against the fact that there could be multiple optimal solutions. And so here's a convex function that has many optimal solutions. Another simple example. I have a1 to an, and I want to find x to solve, minimize 1 over n times the sum of the absolute values of ai minus x. So how do we do this? Can't take the derivative. This is very similar to my ai minus x squared, but I can't just take the derivative. I can take the subdifferential. So x hat is optimal, basically just copying what was on the previous slide. This will happen if 0 is an element of 1 over n times the sum of the subdifferential of this absolute value function, ai minus x hat. What is a subdifferential of the absolute value function? Let's draw it, and that will help us. And so this is the absolute function, absolute value of z. The subdifferential is equal to, what happens if we're over here? Well, this is actually, it's just a gradient, so it's equal to minus 1 if z is any value less than 0. It's equal to plus 1 if z is any value greater than 0. And what about down here at the bottom? If we're down here at the bottom, what slopes can we choose that globally underestimate our function? anything between minus 1 and 1. So it's equal to some value w, where w is between minus 1 and 1 if z is equal to 0. So as an exercise, apply this definition of subdifferential to the above problem to find the solution. You see, it's not quite as easy. This is now a relationship that you need to explore and see what values satisfy this. It's not exactly as simple as an equation as we had in the previous example, where I get it, I solve it, I find out that x is the average in that case. So think about this, and this is a good opportunity to exercise this definition of the subdifferential of the absolute value function. And I'll just give you the answer. The solution is, you can pause it if you like, not the average, but the median of the a's. So all this tells us is that the same way that the mean has a characterization as the optimal solution that minimizes the sum of squares, the median also has a characterization in terms of convex optimization. It's the optimal solution that minimizes the sum of absolute values. Now let's apply this to a problem that's going to be with us for a big part of this course, and is very important. We've already seen it a number of times, and it's called Lasso. So this is very similar to our least squares problem. Again, I'm going to switch notation back to x and y's being our data and beta being the optimal solution. So we have yi and xi. You should be a little more careful here, just so you know that y is the label and xi is rd, and rd is the feature vectors. And I want to solve 1 over n times x beta minus y squared. This was my ordinary least squares problem, but I'm also going to regularize it. So I'm going to put lambda times beta 1, the 1 norm. We'll recall that this 1 norm is defined as, that's what the symbol means, the sum of the absolute values of beta I. So what is an optimal solution here? So beta hat is optimal if 0 is an element of the subdifferential of this whole thing. Remember that derivatives, the derivative of a sum is a sum of the derivatives, and the subdifferential is exactly the same. This first part is smooth, so I can just take the derivative of this. So this is equal to just 2 over n times x transpose x beta minus y plus lambda times the subdifferential of beta 1 hat. In other words, beta hat is optimal if there exists some vector z with the following: zi equal to the sign of beta hat I if beta hat I is different from 0, or any value in minus 1 to 1 if beta hat I is equal to 0, and 0 equal to 2 over n x transpose x beta hat minus y plus lambda times z. Is this enough for us to solve beta hat? Not quite. Not quite, but it is a characterization that's very useful. So we've talked so far about a characterization of optimality for convex problems that are not constrained. some differentiable or non-differentiable. So it's time to move to the setting where we have constraints. And we need to come back to the tangent cone and the normal cone. So remember what these look like. If this is my set X that I'm optimizing over, the tangent cone is basically the cone of directions that we can move in. At a point that's on a curved boundary, it's basically this entire half space. Similarly with here. But for a point, the tangent cone is basically this cone that contains the set. So this is the tangent cone. I'll draw my normal cone in a different color. The normal cone is the set of vectors that make a greater than or equal to 90-degree angle with everything in the tangent cone. And in this case, the tangent cone is actually bigger. So this is the tangent cone and the normal cone. And in terms of notation, I'm going to use T subscript x at x to denote the tangent cone of a set x at the point x, and nx x to denote the normal cone of a set script x at a point x. So we finally come to our more general problem. Minimize f of x subject to x in x. Again, everything in sight is convex. F is convex, x is convex. So let's think about what can we say about optimality? So here's my set x and my function. So I won't represent my function with contours at this point. I'll just pick a particular point and ask, what do I need for that point to be optimal? So what do I need for this point here to be optimal, right in the center? Well, you can see that I can move in any direction. The set x is not a constraint. So this is really, for this point to be optimal for this problem, it should also be optimal for the unconstrained problem. For x1 to be optimal, we need the gradient of f. Well, let me write it more generally here. We've already learned how to deal with non-differentiability. I need 0 to be an element of the subdifferential of f at x1. Okay, this is really just like what we've been talking about. But let's look at a little bit more interesting case here. How about x2? What do I need for x2 to be optimal? So you can see here that it doesn't necessarily have to be that the gradient is equal to 0. There could be directions that improve. And it could be that if you move in some direction, then you improve. But you cannot move because the constraint is active or binding. So what do we need? I'm going to draw the tangent cone here. So this is the tangent cone at x2. What directions are locally good for me? Well, there are any directions that seem to make progress with respect to the local geometry of my space. Anything where I can roll down even just a tiny bit. And what are those directions? Those are the directions where the gradient that have a less than or equal to 90-degree angle with the negative gradient. So from x2, for x2 to be optimal, I need every direction of allowable movement. So I can go in any one of these directions, and all of these directions should be worse off for me. So what does that mean? Every direction of allowable movement should have a greater than or equal to 90-degree angle with the direction I most want to move in, which is the negative of the gradient of x2. Another way to say this is that the negative gradient of f of x2 should be in the normal cone at x2. The normal cone for this example is this. So as long as the negative gradient points in this direction, well, you look at all the directions that you're allowed to move in and they're not desirable because they're requiring you to go opposite to the negative gradient. They're asking you to go according to the gradient, which would just increase your function. Unwrapping this, we have our basic definition. X hat is an optimal solution to star. This is our main problem that we care about, is the same as saying that 0 is an element of the subdifferential of f at x hat plus the normal cone. Where did this happen? How did this happen all of a sudden? Just look at what's underlined here. Minus the gradient is an element of the normal cone is exactly like saying 0 is an element of the gradient plus the normal cone. And all I did to get to my general definition is just swap the subdifferential for the gradient. So we've characterized now optimality for general constrained optimization problem. We'll stop here, pick it up next time.